In this module, we'll cover some of our Moldflow design principles. The goals of this module will be to review the Moldflow design principles, which we recommend that you use in conjunction with our Autodesk simulation Moldflow tools. Why do this? Following these Moldflow design principles can reduce problems with your part and mold design, which will make your life a lot easier when you come to mold your part. Following the Moldflow design principles will help prevent you from doing this, basically throwing darts at a board until something hopefully works. The first design principle we have is to produce a unidirectional flow pattern when possible. When you do this, it also produces a unidirectional orientation within your part. So you can see our top image here. The orientation is different directions, causing flow marks, high stresses, and warpage. In our image below, the orientation is in one direction with uniform shrinkage and stresses throughout the part. Now naturally this is a flat plate, so it's easy to say with this component, but you can apply these principles to your parts as well. We'd also like to achieve a balanced flow. What's this mean? All the flow paths within a mold should fill at the same time and with equal pressure. For multi-cavity molds, this means each cavity should fill at the same time. Within parts, the same holds true. The extremities of the part should fill at the same time as well. There are two types of balanced runner systems typically. One is the naturally balanced runner system, which sometimes people call a geometrically balanced runner system, and artificially balanced runners. In a naturally balanced runner system, the flow length from the sprue to each of the parts is the same for all the cavities, as shown in the image below. Generally, this type of runner system has a larger processing window than artificially balanced runners. We'll take a look at some examples of artificially balanced runners in the next slide. The artificially balanced runner system achieves its balance by changing the size of the runners. This is a very useful technique for balancing runners, as there's generally less runner volume required than the naturally balanced runner. However, due to the changes in the runner diameter, the processing window is smaller than the naturally balanced runner. Injection time is typically the main limiting factor. As a result, in situations that have high runner pressure drops, plus low part pressure drops, tight tolerances, thin sections in the part, and potential sink mark issues, artificially balanced runners may have a very small molding window or may not be practical at all. The greater the runner length ratio between the longest and shortest path, the greatest the potential problem. The following image shows a great example of an artificially balanced runner system. We also like to see a constant pressure gradient. The image in this slide is a good example of what you do not want to see. The XY graph is the pressure at the injection location for this component. Just at the beginning of fill, there's a spike in pressure. However, the big problem is at the end of fill. The part is mostly filling by a radial flow. As the flow front meets the center of the sidewalls, the flow front starts contracting. This corresponds to a slight increase in the pressure gradient. The big spike occurs when 3 corners fill and the remaining upper right corner is the only area that remains unfilled. All the material coming from the gate at this time enters that upper right corner, causing this pressure spike. The volumetric flow rate entering the part is still constant. However, the pressure gradient is an indication of a balance problem. So this might suggest that if this is our part design, we may need to put in some type of profiled injection velocity to resolve this issue. Another thing you'll want to be aware of is your maximum shear stress seen within your part. The critical level really depends on the material as well as the application of your part. We list some limits within the material database for each material. However, these are generic limits. So for parts used in harsh environments, such as elevated temperatures, under a high load during use, or exposed to chemical attack, the limit specified in the database may be too high. Alternatively, if the part is not used in a harsh environment, the limit is typically conservative, and these stresses can be exceeded without many issues. It's just something to be aware of though. If you are seeing issues with shear stress, there are a few things you can take a look at. Your wall thickness, for example. Increase your wall thickness to reduce these stresses. Your flow rate. Lower the flow rate, locally or globally, to reduce stresses. To reduce them locally, you could do that or accomplish that through maybe using a profiled injection velocity. You can always take a look at your melt temperature as well. Increasing the melt temperature will typically lower the shear stresses as well. If you're still having issues, then you may need to reevaluate your material selection. We'd also like to strive for uniform cooling in your parts. When cooling a part, the mold surface temperature should be uniform on both sides of this part. When the temperatures are not uniform, the molecules on the hot side have a longer time to cool, so they shrink more than on the cooler side. This essentially creates a tensile force on that warm side and makes your part bow towards the hot side of the part, as shown in this image below. Here's another good example why uniform cooling is important. This image shows a box-like structure that resembles maybe a lot of parts that are commonly produced today. In this box structure, there's an inside corner which is in contact with what we call the core of the mold. This is normally difficult to cool and where heat tends to concentrate naturally. So, on the other hand, the cavity side of the tool is easy to cool. There's a larger volume of mold to absorb the heat from the plastic essentially. As a result, the inside corner runs much warmer, allowing more time for the molecules to cool down and shrink, therefore collapsing the corner in a bit. This will essentially pull in the sides of the box towards the core, as you can see in this image on the far right. We commonly call this corner effects. Another thing we'll discuss in a little more detail are weld and meld lines. The key differentiator between the two is that a weld line is formed when two flow fronts typically meet head-on. A meld line is formed when the flow fronts meet while flowing in the same direction. So you can see the difference between the two in the image below. Weld lines are generally weaker and more visible than meld lines, but they should both be avoided when possible. Every time a gate is added to your part, an additional weld or meld line is formed, and so eliminating extra gates when possible is advisable. When the number of weld and meld lines cannot be reduced, they should be placed in the least sensitive or least critical areas with regards to their strength and appearance. Depending on the application, a weld or a meld line could be a big problem in terms of either strength or appearance. The strength of a weld line or meld line is generally improved when they are formed at high temperatures and when the pressure to pack them out is high. So, again, if you cannot avoid them, then place them in more ideal locations, away from critical areas and areas of high appearance, as well as maybe hopefully get them to meet at higher temperatures and higher pressures to improve their strength. Another thing we'd like to be aware of are any areas in the part that could cause hesitation effects. Hesitation is an unintended slowing down of the flow front. So when this flow front slows down too much, it gets cold, and in severe cases can even freeze off. This is what has happened in the top image of the example on this slide. Hesitation will occur when there is a large variation in wall thickness within the part. In this case, the rib is much thinner than the nominal wall. Having a fast injection time can minimize hesitation. This increases shear heating as well as provides less time for the material to hesitate in this rib. Another way to reduce hesitation is to gate as far as possible from thinner areas, as was done in the bottom image below. We'd also like to avoid underflow. Underflow occurs when a flow front changes direction during filling. In the image below, you can see the underflow occurs because the flow front is not balanced due to the gate location. The contour lines in the velocity arrows should be perpendicular, as they are in the upper left corner of this image, indicated by the green circle. In the lower right hand side of the figure, they are parallel, indicating significant shift in the flow front direction, which you can see indicated by the red circle. The main issue with underflow is its effects on the part's orientation, or the molecular or fiber orientation. The initial filling direction for an area on the part is represented by the filling contour lines that you see here. The flow direction is perpendicular to the contour lines. The molecules are initially oriented in the direction of that flow. If later on, during the filling phase, the flow direction changes, the molecules closer to the center of the flow channel are oriented in the new flow direction. Molecules want to generally shrink more in the direction of the orientation. And so, if there is underflow, there is significant internal stress in the location of the underflow. Flow leaders and flow deflectors can also be a useful tool for you. So, flow leaders are local increases in your nominal wall thickness, whereas flow deflectors are the opposite. They're local decreases in your wall thickness. So, many times a part cannot be balanced by gate placement alone. It is useful to slightly change the wall thickness to either promote or retard the flow in certain directions. This will allow the filling of the part to be balanced, even though the flow lengths from the gate to the extremities of the part are not equal, as you can see in this image below. We also want to make sure we have our frictional heat under control. Shear heating occurs in your feed system, and it's not necessarily a bad thing. It can actually be advantageous for several reasons. For one, it reduces the pressure to fill the part by increasing the melt temperature entering it. It also reduces the shear stress in the part because of the melt temperature is higher. You can also typically run lower melt temperatures, resulting in longer residence time in your barrel before your material starts to degrade. The amount of shear heating is typically controlled by the size of your runners. The smaller the runner, the more shear heat typically. So if you're following the best practices that you'll learn a little later, when you optimize your melt temperature, it's typically done with only the part. So the feed system's not modeled at this time. So it's important to be aware of this concept because when you add your feed system and adjust your injection location to the top of the sprue, your melt temperature will actually be higher as it's entering the part. So we may need to reduce the melt temperature in your process settings. So in this case, in the image below, if we want to see 234 degrees Celsius melt entering our part, then we'd want to decrease your melt temperature in the process settings to 225 degrees Celsius in order to achieve that. So, again, control your frictional heat and leverage your feed system. Another thing we want to be aware of is the thermal shutoff of your runners. So, the runners should be sized so they allow the parts to fill and pack without controlling your actual cycle time. As a general rule of thumb, we'd say that we don't want your runner to freeze off any less than 80% of the actual freeze time of your part. This ensures that your gate does not freeze off prior to finishing your packing and adequately packing that part out. On the other hand, we do not want it to be more than 200% of the time it takes your part to freeze, because then your feed system is controlling your cycle and therefore wasting time. And for our final design principle, you want to make sure you have an acceptable runner to cavity ratios. What does this mean? The ratio of the volume of the feed system to the total volume of the cavities should be as low as possible. This is to reduce the material being wasted in the runners, and this will in turn reduce the amount of regrind that you have to deal with in the end. In the following image, the runners cannot be made much smaller and still maintain a balanced fill and acceptable packing. So, in this example, the ratio of the runner to cavity volume is 85%. This is pretty high. Ideally, the volume of the runner should be 20% of the part volume or less. When possible, maintaining a unidirectional filling pattern is typically optimal, true or false. The following image is a good example of what type of feed system. A subtle increase in a localized area of your part to promote flow is known as a. The melt temperature you specify for your process in Moldflow is done prior to adding the feed system, so you may need to decrease your melt temperature to compensate for shear heating once the feed system is added. True or false? The maximum shear stress values listed in the material properties are generic limits. True or false?